Thank you to the organizers for inviting me to give a talk here. It's my pleasure. Yeah, I will talk about generative diffusion models, and I adjusted the title a little bit. It's now Inspirations from Physics and Applications in Digital Content Creation. So I'm not sure if, who am I? So I am actually a former physicist doing StatMech, biomolecular dynamic simulation and this kind of stuff, but I basically turned into a generative AI researcher at NVIDIA. So these days, what I'm busy with is I generate stuff like that, you know, funny images, entertaining videos, or 3D objects. So the thing on the lower right is a 3D-dimensional object. And I do all this with diffusion models, which brings us to physics again. These models, have recently taken off. Anyway, so what should you expect from my talk? So I thought a little bit about what I should talk about today. Considering this heavily physics-focused audience. And I in particular want to talk about one work, this score-based generative modeling with critically damped Langevin diffusion, which is a work which is just heavily inspired by physics, and I think is a kind of a nice example of how like ideas from physics can inspire new ideas also in machine learning. So this is my focus. But I will first start with a brief introduction, and if there will be time left, I will give a bit of an overview over all this image, video, 3D kind of stuff that we are doing. But honestly, like, let's see if we'll get there. So diffusion models, a brief 5-minute intro to them. These are also known as score-based generative models sometimes. And they have recently taken over generative learning of like in the visual domain, image generation, and this kind of stuff. And mostly I will talk in this about image generation or explain things in the context of image generation in that talk. It was probably around 2021 where like, before diffusion models, it was generative adversarial networks that were most popular. But I believe the title of this paper says it all. Diffusion models beat GANs on image synthesis. More recently, it's in particular these large text-to-image generation systems that generated a lot of attention, where you can give really creative text prompt to your model, and then the model creates really cool outputs like this hedgehog sitting in a small boat here, and yeah, check out the prompt yourself. This is NVIDIA's large text-to-image model, but even that is already half a year old, and if you look at the most recent results, it's kind of mind-blowing what you can generate. So this is Stable Diffusion XL. This is not NVIDIA, but these are just a bunch of images. They are all like AI generated by the latest models out there. I think it is quite impressive what you can do there. Just to give you a bit of an idea. Anyway, so how do these diffusion models work? So what we do in a diffusion model, we have a data distribution. This could be data images of cute cats, but for the sake of explaining things, we can also think about a one-dimensional toy distribution, like here on the left-hand side. Then you take samples from your data distribution and you diffuse them forwards. You add noise to them. This diffusion process can be described through a stochastic differential equation, which is shown here on the lower right. That is one equation. So you basically take an input, you simulate this differential equation forwards, and eventually you converge to pure noise. So this converges at its equilibrium distribution to a standard Gaussian distribution on the right-hand side. So here in green, you see like some of these diffusion paths. In the background, you see the marginal distribution, how it evolves from the left-hand side to the right-hand side. Here on images, you kind of add more and more noise to it. So the crucial idea is that you ultimately converge to a distribution which is analytically tractable, unlike the data distribution, which is only empirically defined through your training data. So this is a forward process in a diffusion model. Here's a little visualization again. But this just transforms data into noise, but this is not generative modeling. Generative modeling is transforming noise into data. It's the opposite direction. So what you really want to do is to do that, what you see on that slide, you want to go the reverse direction. You want to sample noise from your Gaussian prior distribution and simulate backwards. And there is this beautiful theorem that people first used in like 2021 in this Song et al. Paper, or like also some other papers before, that corresponding to this forward diffusion process, this stochastic differential equation here on that slide, right, on the lower right, there is a corresponding backwards differential equation, stochastic differential equation, that exactly describes the evolution in the reverse direction, what we see here. So what we could do now is just sample random noise, plug it into our reverse time stochastic differential equation on the lower right, simulate it, and generate noise data from noise. Well, it's obviously not that easy, because if we look at this stochastic differential equation, we have this dependence on this one term here, this red term on the lower right. So this is the score function of, so the spatial gradient of the logarithm of the marginal diffused data distribution. So QT denotes like the marginal distribution. You can think about slices here along different times of this diffusion process. This is the score function, and we don't have that. So that's what we need. And training a diffusion model basically all boils down to learning a neural network model of that object somehow. This is what you do when you train a diffusion model. And once you have that, you can generate data. So how do you do that? You can do this with denoising score matching. So, and denoising score matching works as follows. So you first take a diffusion time, T, from this expectation somewhere along your diffusion process. You also take a data sample X0 from your data distribution. Now, this particular one data sample, you diffuse forward. So you kind of initialize your stochastic differential equation that describes a forward with this one data sample. This gives you a Gaussian distribution. And this is this distribution QT given X0. So this, I've heavily emphasized the conditioning here. That's important because this is just a Gaussian, and you can, this is analytically available. So we can calculate the score of this conditional distribution. So this is just this one data sample. And now this noisy sample, you give it to your neural network as theta here, and you let it predict that score. But to each, corresponding to each xt, diffused xt, there could be multiple x0 that, diffuse towards this one diffused data point. So there's some kind of averaging going on. And after the expectation, the minimizer of that objective is actually the marginal score. So so basically if you train like this, well, with all these expectations, sampling over all your data, ultimately your neural network will learn this marginal score. And once you learn this is one slide back, you can plug it into your SDE, numerically solve it with your favorite SDE solver, and generate data. So this is basically diffusion models in a nutshell. I want to emphasize, so this is the score function perspective to diffusion models. So initially, these were also introduced in a slightly different way using variational inference. So in the initial works by Jesher Sol-Dickstein, who was also here, and later Jonathan Ho, who scales this up significantly, and a little bit later, so they used another way to derive this, but at the end of the day, the objectives and the equations are pretty much the same. Since for this audience, it's also interesting to think about diffusion models a little bit from another physics perspective, you're basically minimizing a free energy difference between the data and the noise states on these two different sites. And you kind of learn a non-equilibrium generative process because you, in a non-equilibrium manner, go through these different states. And you kind of perform work on a system when you generate your data to bring it from state A to state B. So the work that you perform might be bigger than the actual free energy difference. So you kind of want to go as slowly as possible to have like a quasi-static process going on there. And this is like the physics perspective of why sampling from these diffusion models is kind of slow, because you have to do it like in really small steps. So this is like 5 minutes intro to diffusion models. I want to point out, if you're new to diffusion models, together with Richie Gao from Google DeepMind and my colleague Arash at NVIDIA, last year at CVPR, we gave like a super long diffusion models tutorial. It's on YouTube. It's 4 hours long, collected already 70,000 views. Check it out if you like, if you want to learn more about diffusion models. Now, before I dive into our more interesting work, are there any questions? Yes, please.
So when you solve this process, are you solving it like as a continuous process, or do you discretize into different steps?
So there is a forward process and there is a backward process. The forward process, you can solve it analytically, and you can, because you can solve it analytically, directly sample from the distribution at any time t. So that's fine, but the reverse process involves this neural network. So it's a highly nonlinear function in there, and this is not solvable analytically. So for the reverse process, once you're given the neural network, you have to always do it iteratively by discretization. And then you precisely run into these issues that a coarse discretization would introduce errors and noise into the system. I mean, discretization errors, or like, you know, you want to quasi-static process, there are different perspectives. All right, then I'll continue. So now in this work that I mentioned earlier, we asked the question, how can we improve diffusion models, right? And well, let's just look at the diffusion process itself at first, right? So what we do in these diffusion models, it's very naive. We just add noise to it. So can we maybe do better? And I kind of want to tell the story here, how it evolved a little bit and where the ideas and inspirations came from. There are different ways to approach this, to be honest. Yeah, so how can we kind of best reach this quasi-static limit in practice, you know? So in other words, because in practice, we cannot generate infinitely slowly, right? So let's imagine somehow this forward diffusion process was somehow more invertible by construction. I know this is hand-wavy, but this is kind of the direction I want you to think into. You know, then it would maybe also be easier to invert without some sort of excessive heat loss because you do like two big steps and so on. So then let's ask ourselves really what makes this forward diffusion process hard to invert? Well, it's a noise injection, kind of obviously, because that leads to more uncertainty in the backward generative process ultimately. And because of that, you then require all these small steps. So can we somehow reach this equilibrium distribution, this Gaussian prior distribution really? So this is the equilibrium distribution towards which we want to walk in the diffusion process, while minimizing the amount of noise injection. So this is kind of the intuition we have been thinking into. So could we somehow diffuse faster and smoother, which, yeah, should intuitively lead to easier denoising? And so this point that this noise injection is tightly correlated with basically this difficult to learn score function, right? It's a score function which makes everything hard, for which we need to learn an approximate neural network. You also see this if you look at these differential equations, right? So these forward diffusions, how like almost everybody does it in the literature, they kind of take this form up here, right? And it's this function G that scales the noise injection. So this dW is just the Wiener process, right? We have seen this earlier. It also scales the score function. So if we could somehow set up a diffusion term where like this F would be more dominant, right? And this G would be smaller, it would also mean that the contribution of this neural network term, or like this, the score function term, which is ultimately approximated by a neural network term, would contribute less. This would all be desirable. So this is the direction we want to think into, but how the heck can we do this, right? So we want to develop diffusion models with a diffusion process that requires less noise and is easier to invert. So, but how, right? And now I want to make a big jump. So in my PhD, I did stuff like that. I developed molecular dynamic simulation, yeah, this is just an MD simulation of liquid water. You can also do like molecular dynamic simulations of protein folding. When you do like these types of simulations, you actually run into somewhat related problems. So you kind of need to equilibrate your system, right? It is also an equilibration process that's going on here. You want to simulate at like some thermodynamic equilibrium or like the canonical ensemble at constant temperature. So it's kind of the same, like equilibrating in a diffusion model towards a prior distribution in a way. And yeah, people in molecular dynamics have thought a lot about how to do this for a long time. So maybe we can take some inspiration there. Yeah, I think I just said this basically. So in diffusion models, it's kind of this Gaussian prior distribution that we want to equilibrate towards. And in molecular dynamics, the equilibrium distribution is defined through like a force field or the atomistic interactions in the system. And yeah, we want to go there. And in molecular dynamics, so one crucial part often is, on the one hand, you want to properly simulate your canonical ensemble, but you don't want to mess too much with the true underlying dynamics of the system, which is actually kind of what we're looking for, right? You don't want to just naively inject noise. So yeah, and in MD, people came up with all kinds of techniques. So this is known as thermostating. So thermostats in molecular dynamics are algorithms that keep your molecular system at its equilibrium distribution and efficiently samples this canonical ensemble. And there's lots. So there's Langevin Dynamics is one version. There's like Nuzi Hoover, Anderson thermostats, Barrettson thermostats. You don't need to have to know this. I just want to make the point that there is huge literature which we can potentially use as inspiration. And often these are designed to perturb the system basically as little as possible. And like I just said, that's exactly what we want in a diffusion model. We want to kind of efficiently equilibrate, but we don't just want to naively throw noise at the system. So what can we do? And let's just do the simplest thing possible beyond naive diffusion models, which is basically just Langevin thermostating. So what do you do there? This is just basic mechanics now. This is really not difficult what I'm showing now at the end of the day. So the equations of motions of your molecular system basically just look like that, right? This is just Hamiltonian dynamics here. So the update in x is given just by the velocity. The update of velocity is given by the potential. Note that this velocity is actually just momentum, but in our machine learning paper, we call it velocity because the term momentum is kind of taken already in the optimization literature. And yeah, mass is 1 anyways, or like, you get the idea. So this is just standard dynamics, but if you would just simulate that, you wouldn't actually simulate a canonical ensemble, but rather a microcanonical ensemble from the StatMech perspective. So you add an Ornstein-Uhlenbeck process to the velocity component here, which is just a noise process again. And yeah, this is basically Langevin thermostating. Now that you sample your canonical ensemble, you also properly sample a Boltzmann distribution defined by the potential energy function U of x. Yeah, if you really, you could also do this without the velocity if you're genuinely only interested in the Boltzmann distribution sampling, which would correspond to overdamped Langevin dynamics, where you have this friction constant. Basically, you crank it up so much that you kind of resample the velocity in each step. Yeah, but this is quite inefficient. So nobody really does this in MD, and this really heavily perturbs the natural dynamics of the system. But now let's look at diffusion models. So in a diffusion model, this was the stochastic differential equation describing the forward process. And I mean, yeah, this is pretty much that, right? So what we see is that this is just overdamped Langevin dynamics for like a quadratic Gaussian potential corresponding to our normal distribution, the prior distribution of the diffusion model. And there was also some time rescaling beta and 1/2, but it is that basically. Yeah. So this leads to the question, like, yeah, then let's just do diffusion models with underdamped Langevin dynamics. Let's see what happens, basically. So this is the intuition here. Can we just add a velocity? And now this was basically the core idea of this work here. This is joint work with Tim and Arash. Tim did most of the implementation work here. Big shout out to him, fantastic intern at NVIDIA back then. Anyway, so now we are back in pure diffusion land here from molecular dynamics. And now our forward diffusion process is defined like this. So really, so X is now our data, like this is not molecules anymore, but now maybe images of cute cats or something like that. And this is now augmented through a velocity variable. And yeah, now we have this Hamiltonian component, right? We have just seen that. And additionally, we have the Ornstein-Uhlenbeck process in the velocity, what we've just seen. Now, if we again go back to these 1D toy distributions, which I've used for visualization purposes, it looks like this now. So here in this direction, we have the data distribution and the velocity distribution. So we just initialize this from random noise. And now something interesting happens, right? I mean, which is really expected if you're familiar with all these Langevin dynamics, Hamiltonian dynamics, whatever. The diffusion in the data component, right? It's not as zigzaggy as it was before, but now we have these smooth diffusion trajectories here. And this is kind of what we wanted, right? And yeah, the velocity is still zigzaggy, but we really care about the data a lot. We get kind of this behavior. That's interesting. So let's take a closer look. And one obvious question is also, how should we now choose these mass parameters, this friction constant that we added here on top? Yeah, let's look at a few cases and also compare to standard diffusion models. So in the middle, this is if you do like what's called critical damping. Again, this is just basic mechanics at the end of the day applied to diffusion models. In this critical damping case, you have a nice balance between this Hamiltonian term and the noise injection, and you see that your green trajectories, they mix really fast, right? You kind of see this here. And note that in all three plots, I should explain this more. In the background, the red marginal distribution is always the one that corresponds to the critical damping case, and only the green trajectories that you see correspond to the three different under damping, critical damping, and over damping cases. That makes it easy to compare. So in this case, we see we have fast mixing. Now, what all other diffusion models do is basically that on the right-hand side. And you already see that these trajectories take some ages to really converge to this prior distribution. And this marginal distribution here that corresponds to the critical damping case, it pretty much converges right away. In the under damping case, this is dominated by the Hamiltonian component, and you get this classical harmonic oscillator style oscillatory behavior. You also don't want that. So you choose a critical damping. And intuitively, if you diffuse faster towards your equilibrium distribution, you would think that should have certain advantages in your diffusion model. Anyway, so if we now look at an image generation system here, how does it look like? So your data, just on the left-hand side, you have pure noise, and on the right-hand side, you have data. So your image gets generated kind of as usual, it looks like. And in your velocity, so the crucial thing to note is your velocity is always somewhat noisy, and maybe it's closer to a normal distribution. That's interesting, right? Because ultimately you have to learn scores of the system. And if your velocity is closer to a normal distribution, it might be easier to learn a network for it, right? Because, it's not such a sharp distribution, essentially. Here's another visualization of that, an interactive one. So you can see how, the velocity component always is kind of noisy. So these are some images. And it turns out, because of this interesting structure here, you only need to learn the score of this velocity distribution given the data in these types of diffusion models. You do not have to learn the score of this marginal data distribution X. So this is a consequence of you can do the math and find this, but you will see this. And that is potentially an easier task, right? SF just motivated. And I don't have a proof for that, to be clear, but the evidence kind of shows it that this velocity distribution tends to be closer to a simple Gaussian distribution. So if it's easier to learn this probably means that the neural networks in this critically damped Langevin diffusion tend to be simpler. They might be smoother. But this also means that you can fit more expressive models for the same price, or have less network capacity required for similar performance. So this is an advantage of that scheme. But let me give you some evidence for these claims I'm making here. So let's consider a simple data distribution, which is just a mixture of normals. So this is just 9 normal distributions. That's our data distribution. For that, we can do everything analytically. So we don't need to learn anything. We can just analytically write down our diffusion model, our score functions, and everything. And now we do this twice, once for the standard diffusion model and once for our novel diffusion model. And we compare the scores that we need to learn, usually through neural networks, these ground truth scores, how similar are these to the scores of a standard normal distribution, which would be trivial. And we see that for this critically damped Langevin diffusion case, along the whole diffusion time t, it's everywhere quite a bit closer to a normal distribution. So this is some sort of distance measure that measures how similar your score is to the score of a normal distribution. And it's a logarithmic axis here, so this is quite a large gap, actually. Now you might ask me, okay, sure, you have that, but does this really translate to simpler neural networks? Again, for this toy example, we then fitted some scores using both with a neural network now, with both a standard diffusion model and our critically damped Langevin diffusion model. And you find that these neural networks are indeed simpler and smoother while getting similar performance, where we quantify smoothness in that case just by the matrix norm of the Jacobian of the networks as some metric. You see that along the whole diffusion process. Yeah, the CLD stuff here is has lower Jacobians. Yeah, so that's potentially good. And we only did this for this toy example, but still, I think that's strong evidence. Yeah, so you can fit more expressive models for the same price or require less network capacity. Yeah, before going to the sampling of these models, are there any questions? I'm sure there must be.
Yeah, thanks. This is really interesting. I want to understand if I'm understanding two of your comments. So you said this is sort of microcanonical like, but then you had a friction term, and I wanted to understand if that effective friction term was still preserving the notion of energy that you meant when you said it was like microcanonical.
So once we add the friction, so you get the microcanonical behavior if you only have Hamiltonian dynamics, which is not what we seek in the diffusion model. But once we add the friction term or the friction and the noise term, like both of them to it, this Ornstein-Uhlenbeck process, then we move to a situation where we do not simulate microcanonical ensemble anymore, but the usual canonical ensemble, like a constant temperature ensemble. And this is exactly what you need also in both the diffusion model and often at least in the molecular dynamics situation, right?
I mean, in molecular dynamics, you can come to equilibrium still at fixed energy, right? And, you know, start from some out of equilibrium.
I mean, quite often you do want like constant temperature simulations, but yeah, there are different.
Yeah, it depends what you're doing.
There are quite a few different ensembles you may be interested in. That
okay, so in the end, you're going for a canonical ensemble.
Yes,
in the end.
Yes.
Okay.
Something I also want to emphasize, I forgot to mention. So I explained this all from this with this molecular dynamics motivation, because this is just, I want to tell the story how it happened for us, just as an interesting insight. You can also motivate this with MCMC methods. You know, this is closely related to Hamiltonian Monte Carlo. These methods have also been used for, you know, sampling in MCMC. This momentum term, you can also think about it like gradient descent with momentum, just that you have no noise added on top. Yeah, you can motivate this in other ways. Anyway, so how do you sample from these critically damped? Oh, sorry, I didn't see
that. Sorry. In practice, in neural net, what is the analog of M in terms of practical parameters?
So the M is a pure, like, honestly, we just treat it as a pure hyperparameter. There isn't really any analog in this case. I wouldn't. So basically there is a relation between M and gamma. So these two do depend on each other, but the M itself, it's a little bit hard to give it a meaningful interpretation, to be honest, I think. It is related to somehow the variance with which we initialize the velocity, as if I remember correctly, but yeah, I don't want to. We can discuss more later. There was another question, I think.
In the plot you showed, the X was rather smooth and the V was
yes.
zigzaggy.
Yes.
So now in the updates for X, V feeds in. So what's the intuition for this being smoothed out?
So the thing,
and if I just look at this equation, in the next step, X is just M inverse times V.
So V is still noisy, but the thing is that this distribution of V tends to be close to a normal distribution. It's to a standard normal distribution. And you always have to calculate these or model these score functions in these diffusion models, right? And if that is the score function your target is close to a normal distribution, then it's easy to model, basically. So it's not so much about the zigzagging behavior for the velocity, but more about its marginal distribution. Or in fact, it's more about the conditional velocity given data, which might be a bit more complicated, but our experience show that what I've shown on these previous slides, that, well, indeed, it still is fairly simple. You can think about it also, when you learn a diffusion model, it's almost the hardest part to learn a diffusion model is at very small diffusion times where your data distribution is like highly multimodal, right? So you have all these different very sharp scores because your distribution at this point is basically a mixture of delta spikes, if you want to think about it like this. But at this initialization point, your velocity distribution is by construction just a single Gaussian. So there, at this point where a standard diffusion model is very hard to fit, this model is very easy to fit, actually. So it's most pronounced at small t. For like intermediate t, it all gets a little bit more entangled, but yeah, we can discuss further later, maybe. Awesome. So, so how do you now sample from these models? So this is now the reverse time stochastic differential equation that describes the generative process, right? So this is a bit of a complex beast. It has these different components. First of all, there is this component. And this is interesting. So this would actually be solvable analytically, right? This is just linear in X and V. So yeah, but if it was solvable analytically, that's great. And we wouldn't have to learn any neural networks for that. Cool. But then we have this other term, that is this term. And here S denotes the score for which we learn a neural network. So only that term defines kind of the part of the stochastic differential equation that we cannot simulate analytically. So that's only numerically solvable. But we have already motivated that this S might be somewhat closer to the score of a normal distribution, at least closer compared to standard diffusion models, which would just be minus inverse M times velocity, which is precisely what we add here. So this whole term might be not gigantically large, right? And this is a term that is only solvable numerically. So can we somehow separate out these terms, you know, solve one of them analytically, the other one numerically, combine them and get a really accurate, efficient solver? That's possible. You can use these splitting integration methods. And in this paper, we also derived like some novel fast samplers for these types of diffusion models. This is also stuff that's inspired by physics, actually. People have been using this widely in MD. And yeah, so the intuition is, yeah, I don't have the time to go through all this, I believe. But the intuition here is kind of you split off your propagator, because that is defined through the differential equation, into these two parts, and you kind of alternate between updating with one and the other. This is akin to leapfrog integration in Hamiltonian dynamics, if you're familiar with that. And then when you do this splitting into these two parts and alternate the updates, then one of these parts can be updated analytically, and the other one, only for one of them, you have to make an Euler-based approximation. And this gives you ultimately higher accuracy. And the error mostly stems from this discretization or this decomposition, but less from like discretizing or like having an Euler approximation also on that part that would be analytically solvable. So that is the high-level idea here. Yeah, this allows us to construct faster samplers. We did some experiments with this whole model. Yeah, back then we just generated a bunch of faces, you know, the celebrity data set is quite popular. So you can generate high resolution data with that. Here's some latent space interpolation. People used to do that. So this is a bit far back, like over a year. Yeah, you can do more stuff now. Anyway, we didn't push this too far. Yeah. So what are the key takeaways here? It is really that insights from physics. So this is how I wanted to explain this. Like, it really can help us to build better machine learning frameworks, better generative models. This generative modeling is kind of taking off these days. I'm sure many of you guys have heard about it. And as a physicist, you can contribute a lot. So I think if you're a physicist who also knows AI, like it's amazing. So yeah. Yeah, and in this particular case, it was, yeah, standard diffusion models really just use the simplest noise process possible. And if you look at it a little bit more from the statistical mechanics perspective, you can do a lot. And as I just explained, we really did the simplest thing possible, I believe, just going from overdamped to underdamped Langevin dynamics. And this already gave us all these rich behaviors and allowed us to develop some really interesting models. And I think this is the purpose of this paper was not to push the state of the art. It was more like to inspire new ideas, really. So maybe people can develop even better diffusions with inspirations from physics and StatMech, from inspirations from MCNC, and so on and so forth. Yeah, so this should be the key takeaway. And I think there are many physicists in the audience here, so yeah, go for it. How much time do I have left? Okay, then I will just blaze through some other stuff we have been doing. Yeah, so other things we have been working at NVIDIA is, yeah, these image generation systems. These are often like cascaded models where you first generate low resolution images and then go to higher resolution. Something I've been questioning myself, you know, these cascaded generation systems where you progressively generate higher resolution things. Are there applications in physics where this stuff would be relevant? I don't really know, but I think it's worth thinking about. You know, like I used to work on molecules. Could you, for instance, do like molecule generation where you first start with coarse-grained molecules and then generate atomistic ones or whatever? Yeah, let me skip that. Here are some funny results. You can do stylization in these models. If you give it reference images that have a certain style, then you can generate text-driven outputs in the style of a reference image. Yeah, we have also worked on video diffusion models a little bit. You can do interesting things like that. Yeah, so this is not as mature as image generation. People just started working on that. Yeah, so one very important framework that often comes up is latent diffusion models, where you first encode your data in a compressed latent space where it's more efficient to work with, and only then do diffusion in this latent space. This is particularly interesting for video diffusion because high resolution videos are really a pain to work with from the data perspective. It's hard. Yeah, another paradigm is in video diffusion that you first train on images and only then you fine-tune them on videos. So you kind of first have independent image generation and then afterwards you align these stochastic processes to form a video. Yeah, so yeah, you can do fun things like this, you know, two pandas discussing an academic paper or stormtroopers vacuuming the beach. Yeah, you can also do more realistic videos. I think it's important. So I don't show these for coincidence. So what these videos show is that you have this kind of zero-shot generalization towards compositions that you never see in your training data usually. So it's clear that when we train on this, the training videos, they did not incorporate these videos, but the model learned to combine these different concepts in a meaningful way. So this is interesting. And you see the same zero-shot generalization in these large text-to-image models, for instance. Yeah, and these examples are now like if you want to generate more realistic outputs. And I don't think it's that bad. Yes, this looks pretty decent. These time lapses, sunset, and these rotating grapes. Another very big topic in the field is like 3D generation. You know, if you train on 3-dimensional data, so this might just be shape generation, like stuff like that. So this was also a latent diffusion model. So you first generate a shape latent variable here, then you generate like a noisy point cloud, then you decode it to a clean point cloud. So maybe then you can, come on. You might want to reconstruct a mesh. People in graphics don't like point clouds, they prefer meshes. So this was one work that we did. You can also, if you're given a 2D diffusion model that generates images, you can distill 3D objects from that. That is also kind of an interesting concept. You kind of have some parameterization of a 3D object through a neural network. Like for those of you familiar with this, like a neural radiance field. Then you render this from different perspectives and give your rendering to a 2D diffusion model, which now tells you how likely the rendering is under the diffusion model. You can backprop this into your neural network-based parameterization of the 3D object. And yeah, if you do this from many perspectives and iteratively backprop the gradients into this 3D object, you can synthesize shapes from that. And so these are all like 3D shapes that are generated here. You can also generate entire scenes. So this is a model. So these are not videos, what you're seeing here in that sense. So this is basically a 3D scene, and we're just walking with the camera through this 3-dimensional scene that was entirely generated by a diffusion model. So, you know, full-blown scene generation is very much in its infancy. So you see tons of artifacts here. But the fact that diffusion models scale to 3D scene generation is quite impressive. We also have some work on cryo-electron microscopy analysis. So that is also interesting. So in that case, you kind of, it's for, yeah, protein structure reconstruction. You kind of image it with your cryo-electron microscope. Then you get like different images, slices, and the state-of-the-art method to do this is some sort of autoencoder-based method where you infer a latent embedding that determines the structure. From that, you then reconstruct a three-dimensional object through a neural radiance field, and then you have a reconstruction loss that slices that's on the corresponding slices there. And something you can do is we tried fitting a diffusion model on this latent embedding distribution. Which means that you can then directly learn a diffusion model of this atomistic structure directly from Cryo-EM data. You can do fun things like this. You can do an interpolation in your diffusion model. And now this example interpolates between the open and closed conformational states of the COVID spike protein, for instance. Yeah. Anyway, let me finally come to an end. Yeah, I don't want to summarize now. I have a ton of amazing collaborators at NVIDIA whom I have to thank. Also, we are hiring in generative AI. There are internships and full-time positions available. So if anybody here is a diffusion model expert or Gen AI expert, I'm in Sanya Fiddler's team. My good friend and colleague Awash Vadat is just starting a generative AI team, fundamental generative AI team at NVIDIA. Yeah, thanks.
All right, more questions.
Thanks for the nice talk. Yeah, I'm so fascinated about your smooth diffusion models. But could you also comment out the relation between your models and other smooth generative model alternatives, such as flow matchings and so on?
So yeah, no, that's an excellent question. So flow matching in that sense, it's not a smooth diffusion model in the same sense like that is smooth, to be honest. So flow matching, let's take a step back. In a diffusion model, when you train your diffusion model afterwards, you can convert your generative process from a stochastic process into a deterministic process, which is known as this probability flow ODE. But you only can do this usually afterwards. You have the stochastic generation, and then you go to the deterministic generation. This whole flow matching paradigm is basically a way to just get away with all the stochasticity and directly train for an ODE-based generative model. And it does so in a slightly more flexible way how you interpolate your data distribution and your target distribution. But the curvature of this ODE is still very much similar as in a diffusion model. It doesn't get any straighter or something like this. It still behaves completely like a standard diffusion model. And this is very different from what we are doing here. We are really fundamentally changing the way this underlying ODE mapping is implemented through this introduction of a velocity component. So this is very different.
Yeah, so on the molecular dynamics kind of side that we were showing at the end, so this is like going outside of distribution essentially a little bit. So then the question is, how do you evaluate essentially the goodness of the model? Do you have some additional scores that you kind of look at the quality of this? Because in the end of the day, we need to quantify it when we want to use it for science cases, right?
So you mean that stuff here, right? Yeah. So this was just very exploratory work, and our evaluations were just very visual. So in the sense that you basically train this in a variational autoencoder fashion first, and your baseline really is using a naive Gaussian prior distribution in latent space, which everybody does in variational autoencoders, but really you shouldn't. Because your distribution of the posteriors that are inferred through the encoder, the marginal distribution of those they never match the actual prior distribution, which is the goal of the KL term and the VAE. So you kind of have a mismatch there. If you visualize this, you will see, you can just visualize this, and by visualization, you see that there is a heavy mismatch between this prior distribution. If you would sample from this naive Gaussian prior distribution and you just visualize your reconstructed 3D volumes, you get complete garbage. But yeah, if you actually fit this latent embedding distribution with the diffusion model, everything changes. So this was just more like a perspective work where we just visually showed that there is a huge gap. You really should not use the standard VAE-based technique for generation. And if you actually only for reconstruction, not for generation. And if you want to do generation, you have to fit the diffusion models. But you're making an excellent point. You should use evaluate this more quantitatively. Yes.
Maybe time for one more.
Thank you. Yeah, that's really cool. Maybe just a quick question, a quick comment to the previous question. So we do have now ways of computing evidence without explicit models, so we can compute Bayesian evidence for generative models, for example. Maybe we should chat about that. I mean, this is fascinating work in terms of this smoothing out the distribution and accelerating the diffusion sampling. You didn't give performance. You kind of downplayed almost the significance of the work when you said, we didn't go for state-of-the-art performance and so forth. How much faster is it than standard diffusion, and how much, what are the? Do you have any kind of? Can you say something about how much better it does?
Yeah, no, that's a good question. So the solver that we developed, the natural baseline compared to that would be a standard Euler-Maruyama solver, and the way this is usually compared is you give me a budget of how many steps I can do, and then given that I calculate some performance metrics. So in the limit of many steps, there is not much difference. Euler-Maruyama will just do fine, which is expected. In the limit of only doing very few steps, if you're only allowed to call your network few times, you do see quite large gaps, to be honest. So the fewer steps you have, the larger the gap. So you definitely can see like 2, 3, 4 times speed up there. All that said, so by now people have developed like methods that are like even faster than that for standard diffusion models, but these use additional tricks. If you combine these additional tricks within these faster diffusion models that we have here, you can get even faster, but nobody has done that yet. But this field is moving crazy fast. So even within the last half year or year, much has happened there. So we do not get state-of-the-art result now, but it's very complementary, these ideas, to these other state-of-the-art methods that have come out recently. Other than that, regarding sampling speed, I also made this point about networks being easier to learn. So at least when we released the paper, we saw that given the same network size, we did get state-of-the-art performance on some image generation metrics. Again, by now this has been outperformed, but largely with complementary methods. There has been some follow-up work specifically regarding this critically damped Langevin diffusion, but not a lot, because I think we need more physicists in the field in generative AI who embrace that kind of stuff. Yeah.
So the stormtroopers vacuuming the beach begs the question, have you asked it about stormtroopers combing the desert? And does it generate the Spaceballs joke?
I have not, but it's a good idea. I should try it, yes.
Okay. All right, let's thank our speaker.